Okay, welcome back everybody. We're getting on to the second half of section 4.3, which was classification of second order linear PDEs. And I described the definition of all the common classifications, elliptic, parabolic, hyperbolic, as well as how the Holy Trinity interacts with those in the last video. In this video, we're just switching minds to talking about why we're even classifying in the first place. So I kind of mentioned this goes back to our notion of the non-characteristic condition, which really has its heart in calculating derivatives normal to the boundary, right? So in terms of second order PDEs, we're talking about calculating the second order derivative, both in the direction of the boundary, right? So if like partial vector n is my directional derivative in the direction normal to the boundary, then, you know, this one that I'm calling nabla partial omega perp squared, this is really defined as the directional derivative in the direction of the normal squared. So it's two derivatives in the direction of the normal. So the question is, can we calculate that from the PDE plus boundary conditions? Right, the answer should be yes if we have some notion of a non-characteristic condition, just like in first order PDEs. So what am I saying? This looks the exact same as the way I had set up the non-characteristic condition in the first order PDEs. That's back in section 3.3 if you want to go back there. But the difference is that now my PDE is second order linear rather than first order arbitrary. Second order linear, and I'm saying that you can compute the second derivative, second directional derivative in the normal direction to the boundary. You can compute it as a combination. This is a combination of all of the other information you know. You can compute it as a combination of all the rest of the information if and only if this is determined only by the very top term, the a, if and only if the normal vector n dot a acting on n is non-zero. And really, if you repeated the whole procedure of the non-characteristic condition from section 3.3 just for one higher order of PDE, you would exactly recover this condition, because dependent on it being a linear PDE, this is actually equivalent to the condition that we have for the non-characteristic condition in first order. So we're just going to be looking at the outward unit normal vector, taking a dot product with an itself, as long as that's non-zero. It has to be non-zero everywhere on the boundary, right? So everywhere on the boundary. But so long as it's non-zero everywhere on the boundary, then we're good to go. I do have a proof of this here, because we have to, you should technically verify that you can actually solve for this second order outward unit normal directional derivative. So I do go ahead and prove that it can be computed if and only if it's satisfied. But I don't think the proof's particularly useful for most people taking this course. And then we just move farther ahead to say, okay, this second order derivative is actually important. The second order derivative in the direction of the boundary, perpendicular to the boundary, is actually pretty important, because once again, it's what determines kind of existence and uniqueness of the solution to the PDE. So we do care about that, and we're going to give it a name, the exact same name we saw in section 3.3. It's going to have the name the non-characteristic condition. So long as this quantity, the normal derivative dot this matrix acting on the normal derivative, as long as that's not equal to 0 for every x in the boundary, we say we've satisfied the non-characteristic condition. So just like in section 3.3, I'll give an example where we can verify this. So let's look at the following second order linear PDE, and we'll recall from our previous section, how do we find a? We find a by looking at these terms. So we're going to grab those three terms, we're going to construct a out of them. In this case, we're two-dimensional, so a is a function of x and y. On the x squared terms, we've got y squared. On the y squared terms, we've got x squared. And then on the mixed terms, we have xy, and keep in mind, you should always divide the mixed terms by 2, because there's 2 copies of them sitting around in A. So that's our matrix A, and then we always have to pair PDE with its domain, and therefore boundary. So we've got our little domain and boundary there, which is really x squared plus xy plus y squared is less than 1 as the domain, and of course equal to 1 would be the boundary. And we go ahead and construct, if we move terms to make this greater than 0, we get that function. And starting with that function is what allows us to calculate the outward unit normal. This is according to theorem 1.2.17, which we covered a long time ago. We've got our little outward unit normal here. And all we have to do from this point onwards, now that we've found A, which is what I've already mentioned from before, we found A, we found the outward unit normal, we just need to compute n dot A of xy dot n. And you go through that process. It's a matrix on a vector, dot product of vector. Not the world's prettiest process. You got to sit down and chug along and simplify. This is once again where computer algebra systems can certainly be your best friend. You end up with this function. It's not great. It's not terrible. It's a quartic in x and y. We need to verify that this is non-zero. Okay, so you actually compute it, but now we must verify that this is non-zero. How do we verify this is non-zero on the entire boundary? It's not the hardest, but we do have to be careful. First, we have to let's verify that we never divide by 0 on the boundary. And that's actually fairly easy to verify because you'll notice that term 3xy shows up. So we've got something like 5 equals 3x, negative 3xy. We could solve this for x as x is 5 over 3y, sorry, negative 5 over 3y, and then plug that value in for x here, and you'll find that that's never going to be equal to 1. You can never choose a value for y to make that equal to 1, insofar as real numbers are concerned. Certainly, every polynomial in the complex numbers will have roots. But as far as the real numbers are concerned, we never divide by 0, at which point we're just going to verify that the numerator is never equal to 0. And it's a little bit of work to do this, but this is why everybody here took Calculus 3. What we're going to do is we're going to take two derivatives, and we're going to look at the Hessian matrix and calculate its, so the eigenvalues of Hessian are strictly positive, which means concave up everywhere. That's just of the numerator. And then we know that 0, 0 is a critical point, which you just find by computing the gradient and then setting that equal to the 0 vector. So the minimum is achieved at 0 since we're concave up everywhere. Well, if the minimum is achieved at 0 and that's equal to 0 at 0, and it's only above, right? It's a concave up, and that's the point 0, 0 with a value 0. Then on the boundary, which is out here, then we're definitely not equal to 0. So lots of different ways to justify it. This is why Calculus 3 is important. So go ahead and justify, if you're ever asked to show that this is non-zero, go ahead and justify using whatever means you like to show that some specific function is never equal to 0, at least with the real numbers. Now, why do we care so much about, I introduced this non-characteristic condition in the context of classification? This corollary is kind of the big important part of all of this. The whole overarching idea of this section is that non-characteristic condition kind of determines existence and uniqueness on the interior, and classification determines the directions in which it's satisfied. So the fact that we can classify means that we can also determine cases of existence and uniqueness using the non-characteristic condition. So if our PDE is elliptic, then in fact the non-characteristic condition is always satisfied. This makes our life really easy. We could have just jumped up here at the beginning, looked at A, and calculated its eigenvalues. We would have seen that the eigenvalues of A are strictly positive. And that means that we're elliptic, and so we wouldn't have had to go through any work, because if we're elliptic, then the non-characteristic condition is always satisfied. If we're parabolic, the non-characteristic condition is violated in exactly one direction. And what that means is you do have to calculate whether or not this direction intersects, then you proceed to compute how the direction interacts with the boundary. Because there are some cases where, in fact, the boundary may be perfectly aligned with the non-characteristic direction, in which case you're actually okay, because everything away from the boundary is still good, but otherwise you do have some spaces of maybe non-existence or non-uniqueness. And then finally, we're hyperbolic. The non-characteristic condition will be violated in infinitely many directions, in the case that our dimension is greater than or equal to 3, or in fact two directions when our dimension is equal to 2. So we get a nice classification of all of the non-characteristic conditions specific to elliptic, parabolic, and hyperbolic PDEs. I've got a proof here. It's fairly easy to go through all of the cases and just determine how many non-characteristic directions you have. I guess the main importance is just that in the elliptic case, it's always satisfied. This is what we tend to really look for. This is actually why when we were solving maybe the heat equation with Fourier methods, we only performed the Fourier diagonalization of those terms and not the terms in time as well, because these terms independently are elliptic, but the temporal term is not. And so we're going to find out that elliptic PDEs have a quote-unquote Fourier series. So of course some stuff for a little teaser for chapter 5, but that's really why we care about all of these, is that it kind of classifies the process by which we should try to solve the problems. Okay, and then in a lot of ways, the main theorem of this section, or at least the way that it's normally taught in undergraduate PDEs, is the following theorem, which basically classifies all of the second order linear PDEs in 2 dimensions. So there's an easier way we can go about classifying these PDEs specific to 2 dimensions. This is, of course, I've written it only in the variables x and y. Of course, you can imagine x and t as well, or x1, x2, however you want to think about 2 dimensions. All we have to do in the 2-dimensional case, we don't need to construct a matrix, etc. All we have to do is find the coefficients of the x squared term, the xy mixed term, and then the y squared term. And just those 3 coefficients, we don't care about lower order for the same reasons as earlier. But when we extract those 3 coefficients of a, b, and c, we want to kind of think about these are the a's, b's, and c's from quadratic equations. And we have a difference between the cases when b squared minus 4ac is negative, b squared minus 4ac is equal to 0, and then the final case on the next page when b squared minus 4ac is positive. Okay, so this actually separates the 3 common classifications we have from each other. And it has to do with, at the end of the day, it does have to do with a quadratic formula, because we are calculating eigenvalues of a 2x2 matrix, so that would make a lot of sense. But it's really nice that it's exactly like the quadratic formula would give. So in the event that b squared minus 4ac is negative, then our solutions, our PDE is going to be classified as elliptic. In the event that it's equal to 0, it's classified as parabolic. In the event that it's greater than 0, it's classified as hyperbolic. Now, of course, in the event that these are constant coefficients, they don't depend on space, and you can say it's elliptic everywhere, parabolic everywhere, or hyperbolic everywhere. In the event that a maybe was a function of x and y, or b and c are also functions of x and y, then you have to be a little bit more careful, and you really classify regions within which the PD is elliptic, parabolic, or hyperbolic. So it can vary on regions if they're not constant coefficients, but primarily in PDE's text, we only worry about the constant coefficient settings because they kind of classify everything for us. Now, I've got the proof there. It's kind of everything you'd expect. You do actually construct the matrix A from this PDE, and then you immediately see that the eigenvalues change their shape exactly at the b squared minus 4ac equals 0 situation. So then on either side of that, greater than or less than 0, you have different cases. Got a little typo here. This should be less than and greater than, but the theorem is correct. So we're going to go through 3 examples of these. These are kind of just common ways that you would approach it. Very straightforward. If we're going to find an elliptic PDE, let's just grab the 3 coefficients on the 3 terms of a being 1, b being 2, and c being 3. And then when we plug those all in, we get b squared is 2 squared minus 4ac. That'll be 4 minus 12, negative 8 is less than 0, so we are elliptic. Similarly, we can do the same sort of thing to test for a parabolic PDE by grabbing a, b, and c. Of course, you would want to rearrange these if they weren't in the correct order as given here, but in this case, they're all in the correct order. So a is negative 1, b is 2, and c is negative 1. There you go. B squared is going to be 2 squared minus 4 times a times c. It's going to be 4 minus 4 is 0, which is precisely our parabolic setting. And then in the last setting, when we have a is 1, b is 4, c is 2, we take b squared minus 4 a c. We get 16 minus 8, which is a positive 8. And so we are hyperbolic in the positive setting. Got one last remark, so we're going to finish. This is the etymology. I think everybody's always wondered where are these words coming from, elliptic, parabolic, hyperbolic. It really does come from this last case, or this last theorem that I've got for you here, classification of second order linear in 2 dimensions. Because if we look at this matrix A that results from that choice of A's, B's, and C's that you're going to classify from, the coefficients, and you form something called the quadratic form associated to the matrix. The quadratic form associated to the matrix is ax squared plus bxy plus cy squared. Very closely related to what would happen if you computed the Fourier transform, right? The Fourier transform would give you the negative of this. Is the Fourier multiplier of the PDE. Okay, so if you decided to do the Fourier multiplier version instead, you just get the negative of that, but everything basically stays the same. And that's known as the quadratic form associated to a matrix or associated to PDE. Well, if we plot this quadratic form as a surface what do we get? We get a paraboloid. Paraboloid in the elliptic case. Okay, that doesn't make any sense. Why would you call it elliptic if it's a paraboloid? Well, we're actually asking questions about how does a plane intersect. So we're going to look at the intersection of a plane with the surface. And so the intersection of a plane with a paraboloid is an ellipse. Of plane with paraboloid is ellipse. And so that's why we call those elliptic. The intersection of a plane with, as you call it, a parabolic quadratic form is a parabola, as you can see there. And finally, the intersection of a plane with a hyperbolic quadratic form is a hyperbola. So there's the hyperbola graphed in the intersection. So that's where elliptic, parabolic, hyperbolic are arising from. And in fact, if we want to talk about, I do have one extra comment here about the geometries, the manifold geometries of the three surfaces I've graphed. So not the planes, of course, but of the paraboloid here, of the, I guess that's a parabolic cylinder is usually what people call those. And then over here I've got the hyperboloid. The surfaces, if you calculate manifold geometry curvature, we actually have positive curvature, zero curvature, and negative curvature, which kind of makes sense with those, with the way that we talked about eigenvalues as well. All positive eigenvalues, one of them was zero, and one of them was of opposite signs. So this is why we have this intimate relationship between actually PDEs and metric geometry or analytic geometry. So it's a very cool little aside here to talk about classifications and then actually surfaces of reality, right? Because we saw the wave equation as one of these hyperbolic situations. If you go into the general relativity, you see that actually space-time has a hyperbolic curvature to it. So all of the spatial directions kind of behave in a different way than the temporal direction. Anyway, it's a little bit of an aside. That's all I've got for you today. We'll see you in the next class. Bye.